Good morning. You have me? Good morning and welcome to 2024 Ascent. And I'm extremely pleased to introduce Professor Dante Loretta as our speaker today. Um, and welcome you, of course, to the AIAA von Kármán lecture in astronomics. We're very happy that you could join us for this prestigious annual lecture. Please be seated. And we're going to have to go, and I just mentioned to you, you will have time to ask questions after the presentation. And if that wasn't enough, then I guess that you can catch Professor Loretta after that or during the hallways and so forth. I'm Fred Hadier, Chair of the AIA Honors and Award Committee. This lecture is named in honor of Theodore von Kármán, a world-famous authority on aerospace sciences. The leadership recognizes an individual who has performed notably and distinguished themselves technically in the field of astronautics. It is my distinct pleasure to introduce you to the recipient of the 2024 von Kármán Leadership Lectureship in Astronautics, Professor Dante Loretta, as I mentioned to you. Please allow me to tell you more about him. As a Regent Professor of Planetary Science and Cosmochemistry at the University of Arizona Lunar and Planetary Laboratory, Dante Loretta stands as preeminent authority in near-Earth asteroid research. Throughout his illustrious 30-year career, Dante has been dedicated to unraveling unraveling the mysteries of our solar system's composition and evolution. His journey began in 1992 as a NASA research intern delving into SETI, a program during his final year, the SETI program during his final year let me see, of his college. Graduating from University of Arizona with dual Bachelor of Science and Bachelor of Arts degrees, he achieved the cum laude honors. His academic pursuit culminated in a PhD in Earth and Planetary Sciences in 1997 from Washington University in St. Louis. Transitioning to Arizona State University for his postdoctoral work, Dr. Loretta embarked on crucial research analyzing the mineral composition and formation processes of meteoroids and asteroids. His pivotal move to the University of Arizona in 2001 marked the beginning of his most significant contributions as a faculty member within the historic Lunar and Planetary Laboratory. Dr. Loretta's exceptional work in cosmochemistry led to the selection as the principal investigator for NASA's groundbreaking New Frontier OSIRIS-REx asteroid sample return mission in 2011. The mission launched in September 2016, reaching the asteroid Bennu in 2018, collecting a sample in 2020, and commencing its return journey to Earth in 2021. The sample successfully landed on Earth on September 24, 2023. Analysis of his material has already revealed profound insight into the formation of the solar system and the origin of Earth as a habitable world. We're honored that he's joining us as Ascent at Ascent, and we are eager to hear more from Dr. Loretta on his remarkable mission. Please note that again, after this lecture, we hope to have him to answer some question. Use your microphone, not the QR code, for asking your questions. So Susan will be going around. If you have any question, please raise your hand, and a microphone will be given to you to ask questions. Now I'm very pleased to invite him to come to the podium. And Professor Loretta, it's all yours. The title of his talk is Unlocking the Secrets of Our Solar System's History, the OSIRIS-REx Journey. What a fantastic presentation.
Thank you, Fred.
Thank you so much. So I'll take this one.
What a great honor to be giving the Von Kármán Lecture at the IAAA. I really appreciate the efforts of the award committee, and I want to make sure you realize that this is a team effort. So I'm up here representing hundreds of individuals that have worked for decades, 2 decades, to make this mission a success. So our partners, primarily University of Arizona, project management, system engineering at the Goddard Space Flight Center, as well as some scientific instrument contributions in flight dynamics management and sample science, and our prime aerospace partner, Lockheed Martin, which has done a fantastic job providing us with a really amazing spacecraft for exploring deep space. So what is OSIRIS-REx? As Fred told you, it's a mission in NASA's New Frontiers program. We're New Frontiers number 3 after the New Horizons Pluto Kuiper Belt mission and the Juno Jupiter Orbiter. And the mission name captures the principal scientific objectives of the program. Origins. We really want to understand asteroids as geologic remnants from the earliest stages of solar system history, dating back over 4.5 billion years. Spectral interpretation. There's over 1 million known asteroids in the solar system, with more being discovered every night. We will study the majority of them with telescopes, and we use spectroscopy to try to infer their chemistry and mineralogy. And by returning a sample, we can ground truth that information and do a much better job with our physical chemical characterization. Resource identification. We're going to a near-Earth object, very rich in water, organics, base metals, rare metals. I really love to hear about ideas for resource extraction and utilization in situ, in space, and we are a pathfinder for that kind of activity. Security. We went to the most potentially hazardous asteroid in the solar system, and before everybody panics, the impact, if it's going to occur with a very low probability of 0.057%, will most likely be in the year 2182. On September 24th, to be precise, if you want to put that in your calendar books. And we're a regolith explorer. Regolith is what we call the loose blanket of rock and dust on the surface of these airless bodies, and that's what we brought back. Here is the orbit diagram. The asteroid is named after the heron from Egyptian mythology, related to the deity Osiris and representing the formation of the universe. You can see the orbit. The Earth is in blue and Bennu is in orange. And it is an Apollo-type near-Earth asteroid, meaning that its orbit crosses that of the Earth, and you can see why the impact hazard centers around the vernal equinox, which is represented by this axis right here. The orbit is inclined about 6 degrees relative to the Earth, but it crosses right through the Earth's orbit. And because it takes 1.2 years for Bennu to orbit around the Earth, or to orbit around the sun, they line up every 6 years. So every 6 years, there's a close approach between the asteroid and the Earth. Here you can see the object, the target of our mission. It's about 500 meters, or a little over 1,600 feet in diameter. So think about it as a small mountain in outer space. And I can tell you, when we got there, the surface was a real surprise for us. We had performed an unprecedented astronomical campaign using telescopes on Earth, telescopes in space like Hubble and Spitzer, to try to infer the surface chemistry and roughness. And we had intuited that it was really smooth and it would be easy to sample this target. And then we got there and we saw this pile of rubble. And it's important to remember what we're looking at here. This is not a solid, coherent body. And you can kind of tell that just by looking at its shape. It's got this nearly spherical form. It's achieving almost hydrostatic equilibrium, which is very unusual for a rocky body on the order of 500 meters. You would expect that to be something driven by a fluid interior, a molten interior like the planets have. But that shape tells you that it is behaving in a fluid-like manner, and we'll see that play out over the course of the mission. It bulges at the equator due to centrifugal forces, so material is sliding down. There's a geopotential gradient. This is like the top of the mountain at the pole here, and this is the valley, and it's counterintuitive. This is where the microgravity really messes with your mind. The surface acceleration is about 5 micro-Gs. And so it leads to the centrifugal forces dominating over gravitational acceleration, and material migrates to the equator and piles up and builds that bulge. You can see the giant boulders. The largest one is right here. It's almost fully buried, but it's about 100 meters in diameter. And you can see these large, about 10s to 50-meter boulders marching across the southern hemisphere. This is our very capable vehicle, built at the Lockheed Martin facility in Littleton, Colorado. I actually took my sabbatical in the year 2015 so I could be in the clean room as the spacecraft was being assembled. And it was a really great synergy because the technicians are amazing. They knew how to do their job very well, follow the drawings and build the vehicle, but they didn't know the context of a lot of the components that we were putting on there. So it was great to kind of educate as we were going through, hey, this is the robotic arm that's going to sample the asteroid. Everybody knew that. But these are the spectrometers that we're going to use to characterize the chemistry and the mineralogy, and these are our science cameras. It was a great experience. I learned an enormous amount of aerospace engineering being part of that team. And here you can see us at Kennedy Space Center in late August of 2016 as we're going through final checkouts of the vehicle to get it ready for launch. This is the star of the show. This was where a lot of the technology development was put into place. So here is a 3-meter long robotic arm. You saw it here in the stowed configuration. So that's the shoulder, the elbow, and the wrist, and then the head is inside that protective chamber for launch. And you can see we kept it bagged and under nitrogen purge throughout the entire assembly and test campaign because pristine sample was the driver on the mission. And I know a lot of you could appreciate the challenges we laid down. For example, because we're interested in nitrogen compounds, especially amino acids, which make our proteins, there was no nylon products allowed in the clean room or anywhere near the spacecraft. So you can imagine the Lockheed Martin technicians when I told them all nylon needs to be removed and you have to figure out something else for all these other things. And there's a lot of nylon in these environments, as we learned going through this process. The strategy is to place this device, we call that the TAGSAM head, TAGSAM being the touch and go sample acquisition mechanism, onto the surface, open up one of these gas bottles which contain high pressure nitrogen, and kind of like a leaf blower, just push gravel and dust through the filter, which is what that device is. The gas escapes and the dust and gravel get captured. And then you can see here, this is the sample return capsule. This is the component that will make it back down to the surface of the Earth. And here the robotic arm is articulated to place that filter into a capture ring and then cut the bolts and the tubes and close that capsule up like a clamshell for its return journey home. Fred mentioned the timeline. We do have every year a commemorative poster that celebrates the major mission milestones, starting with launch in 2016. We had a gravity assist in 2017 to do that orbital inclination plane change to get onto the trajectory to rendezvous, which we did in late 2018. 2019 was mapping and site selection. 2020 was when we collected the sample. 2021 is when we departed, and 2023 is when we came home. Launch on the mighty Atlas V in the 401 configuration. It was a perfect ride, very smooth. I think these are some of my favorite shots, but this one is the best because I had a friend who was flying from Miami to New York and looked out the window and took a shot of OSIRIS-REx launching and then sent it to me. He's like, is that your spacecraft going into space? And indeed it was. These are some of the first shots where the rocky horror that we were facing really became apparent. And this drove a huge engineering challenge because precision guidance and targeting of a location on the asteroid was really what we needed to do. We had to get into a location where the average grain size was on the order of 2 centimeters, a little less than 1 inch across. And you can see most of these boulders are on the order of meters to tens of meters with very few areas that seem to be free of hazards and obstructions. At launch, we were using a LiDAR-based guidance system. And it was based on timing. When we crossed the limb, when we crossed certain range to the surface, it would update 2 maneuvers. There was a checkpoint maneuver which started us descending down towards the asteroid surface, and then a match point, which matched the rotational motion, so that we were essentially hovering over a location and then using the tiny gravity field and the residual momentum to deliver us down to the surface. The accuracy on that system was 50 meters. So the engineering team said, Dante, pick a 50-meter circle, and we guarantee we'll get you inside of that. And then we looked at the surface, and there was nothing like a 50-meter patch of wide open area for us to safely place the vehicle. So we had to pivot. We had, as part of our CDR, NASA and the engineering review board said, you need a backup to your LiDAR system because you're going into an unknown terrain. And thank goodness we put in the capability for natural feature tracking using onboard image recognition and correlation. And we kind of put the stubs in, and the full software development really didn't kick off until we got these images. And I called my project manager at Goddard and I said, we're going to need natural feature tracking if we're going to sample this thing. And it was really a great collaboration between science and engineering. The science team was able to build a whole catalog of the asteroid surface, three-dimensional models with photometric functions overlaid on top of that. The spacecraft could would generate on board a predict image and then acquire the real image, correlate the two, using the offsets to update the onboard ephemeris so that it could target very precise locations on the asteroid surface. So remember, we went from 50 meters. By the time we were picking the final site, they said we can get you into something as tight as maybe 5 meters. So an order of magnitude improvement in the guidance, and really the first time an autonomous image-based guidance algorithm had flown in deep space. I won't show you a lot of the chemistry data because I know this crowd's really interested in the aerospace engineering, but this was really an important result and it kind of validated our whole selection of Bennu as the target. So here we're looking at wavelengths in the near infrared, well beyond what we can see with our own eyes. And the asteroid is in blue, and this is normalized. So we take the solar spectrum and then the reflected spectrum and we normalize, and the residual features are due to chemistry and minerals on the surface. So Bennu is generally flat. It's the blue line here. And then you can see it takes this steep drop at 2.7 microns. The signal really drops down, and then it slowly returns to the baseline. And when you get out to these longer wavelengths, it's very noisy. But this drop is seen in some meteorites that land on Earth, some examples of which I'm showing here. And that's due to the hydrogen-oxygen bond. So this was the first indication of abundant water on the surface of the asteroid. And you might be thinking, how is this possible? It's an airless body in near-Earth space. There's no atmosphere. It's not liquid water. It's not icy water. It's water locked inside clay minerals. So these minerals formed through liquid water rock reactions very early in solar system history. That water got captured into the clays, and those hold on to it even at the high temperatures of near-Earth space on a dark airless body like Bennu. I will never forget the first time I saw this image. We went into orbit around Bennu on December 31st of 2018, New Year's Eve. It was great. The flight dynamics team was in tuxes and evening gowns, and they did all of the orbital commanding to get us into orbit, and then they rang in the new year. It was quite fun. Setting a couple Guinness World Records, one for the smallest object ever orbited by a spacecraft, and two for the tightest orbital radius ever achieved. And we still hold both of those, although we broke the orbit one later on in the mission, broke our own record. And then on January 5th of 2019, we were having a science team meeting. We were grappling with the rugged reality of Bennu's surface. And my astronomy lead was flipping through, these are NavCam images. So in addition to the science cameras, we had very wide field of view navigation cameras. And they would take long exposure images to get the background stars, and then short exposure images to resolve the limb and the details of the asteroid. And they would do double navigation solutions, a star field solution and a natural feature landmark tracking solution. And then Carl Hergenrother, who's the astronomy lead, saw this cluster of dots off the limb. and it looks like a star cluster if you don't know your astronomy, but there's no star cluster there. There should only be a couple of stars in that field of view right there. Instead, there were dozens and dozens of them. And then he put the image up that was taken a few minutes later, and this was the surface of the asteroid erupting, particle ejection events. And this was a real panic moment for us. We just got into orbit. We're just learning how to fly. It was the navigation campaign. So really, I was holding the science team at bay. I was like, we're going to get our data, but let them learn how to fly this thing because we're in an unprecedented terrain here. And then all of a sudden, we see that Bennu is what we call an active asteroid. It's kind of like a mini comet. And it reminded me of those early shots from Voyager of the volcanoes erupting on the moon Io. And immediately we thought the spacecraft is in danger. These might be hazardous. These could be bullets that are flying off the surface. They could take out critical components. And so we stayed up all night. I created 3 Tiger teams. They were looking at different safety analyses. And they came back and they said, well, a lot of these are going into orbit. Let's take a look at actually. So here is, you can see the first detections in January 2019. This is a very common phenomena throughout the entire mission. These are all particles in orbit around Bennu. Here's the spacecraft. Here's the asteroid. And we would just see the surface erupt. Sometimes just a few particles would kick off. Some of them were on escape trajectories, so above the escape velocity, which is like 10 centimeters per second. And then you would see these clusters of them all explode at once. And we're like, well, we're in orbit. And just to give you a sense of how slow things move in this environment, it took 60 hours for us to go once around the asteroid, right? Space station goes around every 100 minutes around the Earth. We're moving really slow. And they came back and they said, well, these things are moving just as slow. So you're going to get hit by something moving about this speed. It's really no hazard at all. But it took a while, again, to recognize that microgravity was messing with our minds, and that what looked like a very dynamic, energetic, potentially hazardous environment turned out to be just a few little dust grains. We like to compare it, if you take a cracker and you break it and some flakes pop off, that's about the energy that it takes to launch particles off the surface of the asteroid. So it started out as a crisis, and it turned into a really cool science experiment. And you saw all the orbits that we were able to track. And this was the group at JPL that was on our team, and they're experts at determining orbits for asteroids as you detect them in these telescope surveys. So they were able to apply all the same algorithms and techniques. You had a moving observatory, so that made it a little tricky because the spacecraft was moving relative to your targets. But they were able to reconstruct all the orbits, and they became fantastic gravity probes. So when we launched, we had the requirement to map the gravity field to 4th degree in order. And we were struggling a little bit if we were going to make that because we needed to get in tighter than we were orbiting, and the flight dynamics team wasn't sure it was going to be stable and safe. And then all of a sudden, we had hundreds of gravity probes, and we got the field to 8th degree in order. So we really were able to push down. And the gravity field gives you some deep insights into the interior structure of the asteroid. So the science was amazing. There's a lot of publications about the mission, but we were really there in a tactical kind of mode. And it was a great collaboration between science and engineering. Science was developing all the maps of the asteroid surface and then feeding them through these 4 filters. That deliverability, and I already told you about the natural feature tracking system that we had to update. Safety, is it going to be safe? We were really worried about tipping over and then during the backaway maneuver crashing into a large boulder. Sampleability, were we going to have those small gravel-sized particles on the surface to pick up? It doesn't help if you get to the surface, there's nothing to grab. And then science value, I gave you a hint of that with the water. We also found abundant organic molecules and carbon on the surface. The science value was amazing everywhere, so we didn't really have to worry about that. But we were looking for the sweet spot where all of these different maps, we had maps for each of these parameters, come together to the sample site selection. We got it down to 4. We started with 50 possible locations. It was quite chaotic in the early days. And then we kind of went into a tournament. So we got it down to 16, and then we put them head to head, and 8 were left. And then these are the final 4. And you can see we're looking at craters. This is about 20 meters. This is about 20 meters, 2 20-meter diameter craters. What ended up being the primary site, which we nicknamed Nightingale, and the backup site, which we nicknamed Osprey. We had some other interesting terrain. This is on the wall of a giant crater, and you can see there's kind of a runway strip right here. material is migrating down this crater wall, but this big boulder is blocking any large material from accumulating here. So this looked actually like a neat little landing strip, and I think it would have been a good site. And then a similar, much smaller crater had the finest grain material we could see right there, but it was just too tight of a fit. So the engineering and safety teams were voting for Osprey because there was no large obstructions around it. And science and TAGSAM was voting for Nightingale. And what really made the difference for me was the sampleability map. And I'm just giving you an example of the kind of data products that we would produce. So the scale is a sampleability efficiency. This was really mapped to experiments we had done in the lab, a lot of vacuum chamber experiments, and also some reduced gravity aircraft experiments. All of the different parameters, the size frequency distribution, the largest particle size, the possibility of a tilt of the head. And so blue was really good, sorry. Blue was really good and red was really bad. And here was Osprey, dang it. And you can see right in the middle where we're most likely to land, these are our 5-meter circles here now, was low sampleability, whereas Nightingale had some hazards around it, but right in the heart where you're most likely to land, because this is a Monte Carlo distribution that defines these delivery ellipses, was really nice and clean. So sampleability looked great. That's why TAGSAM voted for it. And then also science looked really good. What safety was worried about was this behemoth on the crater rim right here. This is about a 12-meter tall boulder, so like a 3-story building. And this is the crater that has the really nice sample material. You can kind of get a sense of how rugged the asteroid surface is if you look around the crater, all these giant boulders everywhere. And then right in here, a very fresh, young impact crater exposed what we've learned is a subsurface of much finer grained sample. So it looks like the small material is getting either swept away, leaving behind a really rugged, bouldery lag deposit, or it's kind of percolating down through seismic shaking events driven by impacts like the one that created this. We estimate the crater on the order of 100,000 years old, which is very young in geologic time. And that's good news for the science because that means it hasn't been exposed to the cosmic rays and the high energy photons, which can change the chemistry and mineralogy, especially of the optically active surfaces. And then as a reminder, I love to show this video. This is what we thought was going to happen when we sampled the asteroid. We're going to push that filter head down. You're going to blow that gas, a little bit of rocks and dust. The requirement was 60 grams or about 2 ounces, and then we would back away. And then let's take a look at what actually happened. So here we've got some shots from the SAMCAM, the sampling camera. That's the filter right there. This is the gas bottle. It's in black mylar blanketing for thermal protection. And we're approaching the surface at about 10 centimeters per second, and we're snapping images every 1 second here. We're going to hit right on the middle of that boulder. It's about 20 centimeters across. And you'll see when we make the contact, we push in, and then all heck breaks loose. And the first thing you notice is that the head's going into shadow. So we're digging down into the subsurface of the asteroid. You can see when it comes back out, there's a snowstorm of very fine particles just blowing around everywhere that we look. We were able to reconstruct the event. Actually, let me show you. Here's another camera shot. So this is one of the nav cams now. We're looking off to the side. So you can see this is the shadow of the robotic arm coming in. There's the sample collector. It's going to touch just off the field of view. And that's what the SAMCAM captured. And then we open up the gas. You can see a really fine blast of dust, and then a huge amount of material is mobilized. You can still see the shadow of the robotic arm right there to give you a sense of where we are. And you can see how distorted it is. We're throwing rocks easily 10 centimeters. In some cases, 20 centimeters are flying away from us. And if you look in the upper right corner, you'll start to see the original asteroid surface come into view. But look at the rocks that are tumbling, like this one right here, this one here, this very platey, flaky. It's probably the size of a dinner plate. Big ones tumbling around here. And then as the asteroid surface comes into the field of view right here, first of all, this is a plume. It's like a wave. where we just started forming an impact crater essentially when the tag SAM hit. And then this scallop, you can see there's a line of debris here and a line of debris here. This is where the thruster is hitting. So the thruster is scouring away this region. So, and in fact, there was 4 of these. And then here you can see the rocks flying. These are shadows over the original rock surface. You can see these big particles are still tumbling unaffected by the thruster plumes impinging on them. So remember the little video I showed you with tag SAM hitting a nice solid surface, a few particles that get pushed into the filter, and then we back away. This was a shockingly encounter between the spacecraft and the asteroid surface. We did not expect it to be this dynamic. So we had to reconstruct what actually happened. So we went back to the animation team at Goddard and I said, okay, you got to redo the animation because what we did is not what happened. We hit and we sink. There is no downward resistance to the motion of the spacecraft. So we continue at 10 centimeters per second for a full second before the gas fires. So we're 10 centimeters into the subsurface, which is great for sample collection. And we continue to sink. By the time the thrusters kick on 6 seconds after contact, we're about 50 centimeters down into the subsurface, and we're moving at 4 centimeters per second residual velocity. The deceleration is entirely due to the gas blowing out of tag SAM. There was no deceleration from the asteroid surface. It really was like hitting a fluid, like quicksand, or I use the analogy of one of those ball pits at the kids' playground. And so it was astonishing. We're able to reconstruct the energy of the event and constrain the regolith properties. The bulk density at the site of contact was about 500 kilograms per cubic meter. The bulk density of a rock is like 3,000 kilograms per cubic meter, and those carbon-rich meteorites are like 2,000. So 25% the bulk density of the rocks we expected the asteroid to be made out of. And the cohesion, which we thought would really drive the dynamics between 2 particles, was less than a millipascal. And one of the things we did early on during development was gather all of the world's experts on asteroid science and say, can we constrain any of these properties? Because the engineers need an environmental requirements document to build the spacecraft to. And they came back and they said, there's no way the cohesion is going to be less than a kilopascal. We measured it at most of a millipascal. That's 6 orders of magnitude off in our environmental parameters. And as I like to say, even for a geophysicist, that's embarrassing. And we're geochemists, right? So that happened. It was October 20th of 2020, right in the middle of the darkest days of the pandemic. It all went, we didn't have those images until 2 a.m. So we were only getting 40 bits per second telemetry during the actual sampling event. So these little breadcrumbs, mostly natural feature tracking data, which was phenomenal because it was giving us range to the surface, range rate to the surface, and the probability of hitting a hazard. I didn't mention it, but in addition to using the natural features to update propulsive maneuvers, after the final maneuver during the descent, the spacecraft was still propagating its ephemeris down to the surface, and we had drawn red circles around a lot of those big boulders, anything a meter or larger, and if the spacecraft predicted a likely contact with one of those boulders, it was going to back away autonomously without making contact with the surface. But that all worked. It was great. We got the data back. We were stunned at the imagery, but we didn't really know what it meant at that point. We were even debating whether that was a plume that was moving across the surface or some other phenomena that we weren't sure of. And then 2 days later, we're going into the validation, verification of successful sample collection by putting the tag SAM in front of the SAM cam, so the sampling camera that had the shots going down to the surface. We just put the arm right in front so we could look at the base plate. In addition to the gas stimulation, we had a backup strategy. These are all little pads of stainless steel Velcro. Actually, the loop side of the Velcro acts as little tweezers when we push them into the surface and then back away. And what really shocked us here was that we were leaking sample. And you can kind of see this bright area here is a flap that's meant to keep the sample inside, like a check valve. But it was being propped open by about a 3 centimeter particle right there. And this is all material escaping into space. Remember that our requirement was 60 grams just with the particles that were visible in this field of view. And you can get a sense, these are shadows of particles, like this one is casting this shadow right here. 10 grams of material is being lost. So over the tens of minutes of this photo shoot, we probably lost more than the entire mission requirement. But we were able to expedite the stow. So we said, okay, emergency time. This team was used to it by then. We got the Deep Space Network to line up. You can see us click in, and some more particles are escaping right after we stow. And I was like, I hope those are the last ones that we lose. And then we detached the robotic arm and then closed up the clamshell and got ready for the journey home. Flash forward, so that was in October of 2020. We actually didn't leave until May of 2021. Just like you have a launch window where the asteroid orbit lines up with Florida, you have a departure window where Bennu lines up, in this case, with Utah. We fired those engines in May of 2021, setting up a ballistic trajectory for 2.5 years through the solar system, targeting the Utah test and training range just outside of Salt Lake. And then on September 24th of 2023, just last year, these are the images that we got from the spacecraft after capsule separation. So this is the Earth, the limb of the Earth right here. The sun is up off the field of view. And then that's the capsule. So we detach it. It was on a separation and spin-up mechanism, a coiled spring that was pushed inside the interior of the spacecraft. We released the bolts, and the thing just spun and through the capsule. And it was a dumb capsule. It had no guidance capability whatsoever, so the targeting was really essential here. And you can see it. We were about a quarter of the distance between the Earth and the Moon when that capsule was released, and it was 4 hours of flight from leaving the spacecraft to entering the top of Earth's atmosphere. And this was probably one of the most panic-stricken moments of the entire thing. So at this point, I'm in almost 20 years. I got involved in the program in February of 2004 when we were in proposal and concept development phase. And that morning, I was up for all the spacecraft commanding activities to make sure it was safe to release the capsule. And then a few hours later, I was in a helicopter flying out to the most likely location where the capsule was going to touch down. And I'm listening, and all I can hear is what the range command officer at the UTTR is calling out. And there's a critical crossing, 100,000 feet. A drogue parachute is supposed to deploy because we're making the transition from hypersonic to subsonic flight, and the capsule's not stable on its own in the subsonic regime. And there was a disaster in 2004. The year we started the program, a NASA mission called Genesis, also built by Lockheed Martin, had a failure of a parachute to deploy, and the capsule cratered into the Utah desert. And that was really fresh in our minds. That was our worst case scenario, the Genesis scenario. 100,000 feet. I tapped the officer who's in the front. Any word on the drogue? She's like, they're not calling drogue. There's no drogue. And that was when it was supposed to deploy. And I'm thinking, we're on live TV. Like NASA's helicopter number 2 is NASA's TV cameras, and they're following us around, and I'm gonna have to get out in the Utah desert to this potential disaster. 60,000 feet, no drogue. And then finally, by some miracle, she says, they're calling main chute. And I'm like, what? I was like, how is that possible? How did the main chute come out and not the drogue chute? Turns out we had a wiring issue, and the signal to fire the mortar and release the drogue was switched with the signal to cut the main chute. So we cut the main chute, but the cap was still on, the mortar hadn't fired. And this is where redundancy and margin saved the day, because we got a pressure transducer as a backup. If we hit a certain atmospheric pressure, it just blew the whole system. And so the drogue and everything came out all at once within milliseconds of each other. And thank goodness we got a safe landing of that capsule on the Utah desert, ending 20 years of effort on the program with the successful delivery of samples to the Earth. I didn't have to deal with the disaster. I was able to greet my long-lost friend. Seeing that capsule on that desert floor, I can't tell you what a relief it was, just the profound sense of accomplishment and really gratitude for everybody that had worked to make this mission a success. As I mentioned at the beginning, thank you. We got it on a long line, and we got it onto a C-17. I would say the military was amazing. The United States Air Force, United States Army, the teams at the Utah Test and Training Range were just absolutely fantastic. They flew us in that beautiful C-17 to Ellington Airfield, where we got the capsule into the clean room at NASA's Johnson Space Center. That's the science canister that we're opening up. There's your happy PI who got to lay his eyes for the first time on beautiful black asteroid dust. You can see it rimming around. So here's Tag Sam safely tucked away. This is all sample. And so we got in there right away. You can see these are actually some pretty chunky particles. These are on the order of a couple millimeters. For us, we work with electron microscopes looking at things at the atomic scale. That alone is a phenomenal sample return, and that's just barely what we've got. What we ended up with is 121.6 grams of sample, more than twice what we promised. Jim Green was heavily involved in the early selection and management of the mission at NASA headquarters. And sure enough, there's our 3-centimeter troublemaker, the one that held that flap open that caused us to lose all those particles. So that's just a bit of the story. If you're interested, there's a couple books we were put out. One, Bennu 3D, is a beautiful illustrated guide, all the maps and tons of the pictures. And then my own story I captured in the memoir, The Asteroid Hunter. So thank you for your attention. I think you're on your
The
lapel mic.
Institute's Honors and Award Committee really takes pride in presenting this. This lecture is extremely informative and exciting. Thank you so much for presenting this. It is my great pleasure to present to you on behalf of AIAA a medal and a certificate for the recognition. If you allow me to first give you this on a medal. And give you the medal, the certificate.
That backwards.
Then you hold it, and then so
there you go. Where's up there? Thank you so much.
Because just congratulations.
Yes.
So let's take a picture together.
Okay.
Just hook on Mike.
Where's the camera?
Right. And you put this one again.
Yes.
There we go.
Where's the photographer?
But that is if you're here.
Oh, okay. Sorry.
Okay, we're good. We do have some time to ask some questions. If you don't mind, I ask the first question.
Please.
I have to go and introduce another speaker,
Yes.
which is Sir Martin Sweeting, and another very exciting topic that people are welcome to, after you finish, to come to the next one, which is in 113. So you showed the dynamic behavior of the asteroid, which was pretty exciting. Typically, it is believed that the asteroids have non-uniform rate of rotations, and which is really a tumbling behavior.
Mm-hmm.
And so therefore, as the spacecraft closes in, you have to put yourself into synchronizing behavior in 6 degrees of freedom.
Right.
Did you have to do that? And do you think that it could be because there's no atmosphere, control system has to be so accurate, so is navigation. Can you elaborate on this, whether or not you had to go through this?
Absolutely. So good news is Bennu is not tumbling. So it only has one rotation axis, and it's almost 180 degrees. So it's a retrograde rotator. But what we did see that was really fascinating is that the rotation rate is increasing. Even over our 2 years of encounter period, it's sped up in a measurable way. And that's due to a phenomenon called the Yorp effect, which is named after 4 scientists. But it's the momentum transfer between sunlight and thermal emission that actually causes the asteroid rotation to increase. And it will continue to do that. Its doubling time is a little over a couple million years.
Thank you so much.
Sure.
So is Susan there now with the microphone for people? Questions? There we go.
Right there.
There are a few hands. There's some in the front.
Hi, my question is about after contact. Did you have any photographic evidence of movement by the larger boulders surrounding the crater?
Yes, there was extensive mobilization of the meter scale boulders. One of them we launched about 12 meters out of the crater. It was directly hit by one of the thruster plumes and kind of like kicking a football, just must have popped up. We see some of them flipped over. And then one of the more interesting features was right at the edge where the thruster plume was impinging, there was a ring of boulders. We called it a campfire ring, is kind of what it looked like. So it was moving meter scale boulders without any issue. And these are pretty low Newton, I think 4.5 Newton thrusters. And we had 16 of them, 2 on each corner. Sorry, 8 of them that were fired. The back ones weren't firing. So it wasn't a huge amount of force, but it doesn't take a lot of energy to push stuff around on these asteroid surfaces. The cohesion is so low, the density is so low, and you're in microgravity. It's a whole different astrophysics regime. And as I mentioned, it took us a while to get used to that because it's so counterintuitive to our everyday experience. Yeah, here. Yes.
Yeah. Okay. Can you hear me?
Yes.
Yes.
Just curious, there's a lot of talk about utilizing asteroid resources as we move throughout the solar system. Is Bennu, do you have any insight whether Bennu is representative? I mean, it's often seems, I think people tend to think asteroids as solid rocky objects, and certainly when you get to something like Ceres, I'm sure that's true, but how representative is the kind of collection of dust and grains and particles and boulders for Bennu? Is that a comparable feature we're going to see in a lot of places in the solar system?
Great question. So Bennu was chosen because it was pretty distinctive. I mean, it's a very dark, carbon-rich, water-rich asteroid, and that's unusual in the inner solar system. So compositionally, it's an outlier, and that's what made it scientifically compelling to go there. And I didn't go into the sample science, but it's been amazing, and I'd be happy to talk to people offline about it. But what is common is that all of these small asteroids, especially in the sub-kilometer regime, are rubble piles. That seems to be pretty consistent. I mean, we've only got a handful of them that we've seen so far, but the Dinkinesh flyby that Lucy did, that was a stunning object, kind of in between a rubble pile and a coherent object. But it seems like that structure where you have boulders and gravel and dust just barely held together by their own self-gravity is pretty common. What's going to be different is the chemistry and the mineralogy. Most near-Earth asteroids are going to be very silicate rich, and I'm talking anhydrous silicates like olivines and pyroxenes, if you know your minerals, and metal rich, base metals like iron, nickel alloys. That's going to make up most of the rocky, what we call S-type or stony type asteroids in our solar system. So structurally similar, compositionally very distinct for Bennu.
Hi, I'm Saptashi from JPL. Great talk. I was wondering if you could give some background as to how the idea to tag an asteroid came about. What was the backstory till winning the proposal? And
Yes.
if you had any advice for younger engineers and scientists who would like to have missions like these in the future.
Yeah, the decision to go with touch and go goes back over 20 years in the very earliest stages in 2004. It's an interesting story because Lockheed Martin was the driver of the mission. So the Lockheed Martin Space Sciences division came to Arizona, University of Arizona, and to my mentor, Dr. Mike Drake, and said, we want to partner with Arizona on an asteroid sample return mission. And they'd already been working the design, and they were really going down the touch and go path. And I said, I was brought on as Mike's deputy. Mike passed away in September 2011, and I took over as the PI from him at that point, like 4 months after we won the contract, but that's a different story. And I said, well, let's just take a step back because I want to understand, because I wanted to land. I was thinking, spend some time, survey the terrain, have it grab particular stones of interest. And they were like, what can you tell us about the surface properties? And that's where we started, despite all of this data that we had, we're like, we really don't know. And clearly we still didn't know until we got there what the surface interaction was going to be like. And they were like, you could have harpoons, you can have hold down thrusters. You're in a 4.3-hour rotation period, so your thermal cycle is going to kill you. Literally, you're going to kill your spacecraft if you try to survive more than a couple hours on the surface. And they said by far the lowest risk approach is touch and go. And then we were driven by the contamination cleanliness requirements. We didn't want to have gears or brushes or claws or scoops that was going to have a lot of interaction. The gas stimulation was a very clean way to collect the sample, and it worked really well. I'd say the only real design flaw was not being able to close the chamber. I'm convinced we packed that thing full. Probably a couple kilos were in that at the time of contact, and then the back away with that open valve, I think we lost kilogram of material. So that breaks my heart to this day, that there was, even though we got more than twice what we promised, you always think of the one that got away, right? So, and advice for young engineers, well, first of all, just go hang out in places where these things are happening. There's, Jet Propulsion Laboratory, Arizona State, Colorado, MIT, APL, Johns Hopkins. These are environments where people are coming up with mission concepts, and there's tons of activities that you can get involved in. JPL Summer School is a really famous one to learn how you go through the process. And we've been doing these for a long time. Pretty much any solar system mission you can think of, there's been a concept worked at some level already. So you're going to be hard pressed to go say, geez, has anybody thought about returning a sample of Venus's atmosphere? Like, yeah, actually, we thought about that 15 years ago. Let's pull it off the shelf. And then you can refine it and move it forward from there. So I think that's the best advice, is just go where the action is. And my management has been, principle has been to reward initiative. So come forward with good ideas, show you're willing to put in the work, because this is hard work, this business is not easy. You got to be willing to really push through. Whenever it feels like the wheels are falling off and the design's never going to close and CDR's in 2 months, and you're like, I don't know how we're ever going to make it. Just keep going. Just keep going, because you'll get there if you got the right team and the right attitude.
So I'm Jim Green, retired NASA guy, and you have acquired an enormous amount of information about its dynamics and its structure and how it's evolving over time. So I really have two basic questions. One, where do you think it was originally created, or the bulk of it? And two, what's the possibility that it was a comet first?
Mm-hmm. Great question. So I didn't get into the sample science, but we're really looking at highly hydrated, very carbon-rich rocks. But the really exciting discovery is evaporite minerals. There's evaporite minerals encrusting a lot of the stones here. So we're talking about a world where you had liquid water persisting for a long time, for geologic periods of time. The other big result so far is there's a lot of ammonia in the sample, very high ammonia concentrations. So we're looking at water, carbon dioxide, and ammonia as ices that accreted the original parent body. That means way out, like 10 AU or so, with the original parent body. So Bennu is a tiny set of fragments of a much larger world. We're estimating 100 to 200 kilometers, icy, rocky material, organic rich material that accreted. You had radioactive isotopes, and that drove hydrothermal alteration. And then that body had to wander into the inner solar system, probably the main asteroid belt, and get shattered into the fragments of which Bennu is one of. So more like an Enceladus kind of object is what we're thinking than a comet that hasn't had liquid water in its interior. And it's kind of a continuum, right? How much melting took place before it's no longer called a comet? We haven't really resolved that. But icy body, outer solar system, volatile rich, and migrated into the inner solar system over the past 4.5 billion years or so.
Okay, we do have time for a few more questions. Susan, after that, the gentleman in white. So first, yeah, go ahead.
Hi, I'm a student from Virginia Tech, just graduated. A lot of research has been done to determine the surface property of asteroids and whether or not a spacecraft can properly land and gather good information. Based on your experience with Bennu, how would you estimate the accuracy of that research up till now?
I'm sorry, could you repeat that? I'm having a little trouble hearing you. Just
Oh, sure.
last part.
Based on your experience with Bennu, how would you estimate the accuracy of research on asteroid surfaces until now?
Right, poor, clearly, but getting better. And it turns out that the things that look like boulders, they're not really very coherent. They seem to be really highly porous, very low strength. So we agonized for a year over where to go and collect the sample. At the end of the day, I think we could have probably touched down anywhere and the boulders would have just crumbled underneath us. So we've relied very heavily on thermal characterization, a property called thermal inertia, right? Inertia being resistance to change, thermal inertia, resistance to change in temperature. The asteroid heats up and cools off really quickly, like fine-grained particles normally would, like lunar regolith or sandy areas on Mars. But that doesn't mean flat, sandy terrain. You could have very rough and rugged terrain because of these low densities. So we got the thermal properties right. It was the translation from thermal to grain size that we were way off on. So I think we have to go back because we've done there's been a lot of literature on thermal analysis and grain size distributions on asteroid surfaces. All that needs to be redone. The other thing, and I've been looking for somebody to really want to take on this project, we have a fantastic radar data set from Bennu from the 1999 discovery and the 2005 apparition, where we resolved the surface at about 7.5 meters per spot. And nobody's gone back and said, now that we know the details, where all the boulders are, where the craters are, what was in the radar data that we didn't know enough to interpret out? So there's a real kind of low-hanging fruit project there to say, let's go back to the Bennu radar data using all of the maps and shape models and thermal properties that we've characterized. Because I think the radar beam, one of the other lines of evidence for the smooth surface was the radar roughness measurement. I think the radar penetrated maybe 10 wavelengths, so well over a meter. So you're probing the upper meter of this asteroid surface with this radar, and nobody's gone back and ground truth the original data, now almost 20 years old, with all of the amazing information from the remote sensing campaign. So if you're interested in that, let me know. I've been trying to get a student to sink their teeth into it, but they get scared with the radar data processing, which isn't intuitive necessarily.
Okay, that's all I wanted.
Thank you for an amazing talk. Looking forward with OSIRIS Apex coming up, what are your thoughts on the expected science and opportunity that's coming with the extended mission?
Thank you. Right, so you saw the image of the capsule leaving the spacecraft. The spacecraft did not follow the capsule into the atmosphere. It performed a deflection maneuver and it's still in heliocentric orbit, getting very close. The perihelion is about 0.5 AU. I have handed over mission leadership to a protege, Professor Daniela Della Justina. She's been with us since she was a freshman at University of Arizona in 2005, and now she's the PI of the extended mission OSIRIS Apex, which is going to rendezvous with another near-Earth object called Apophis, kind of an infamous asteroid because when it was discovered in 2004, the odds of it hitting the Earth looked really high, like a couple percentage. That's all been retired with better observations, but it's going to come within 30,000 kilometers of the Earth in April of 2029. You might be able to see it with your own eyes if you're in Eastern Europe or Africa, because that's where it'll do its closest approach. The spacecraft will not only get there, but it'll be able to go into orbit around Apophis. We can't collect a sample because the sample hardware is on Earth, but it has all the cameras, all the spectrometers, half the LiDAR. We did lose one of the lasers. It was the only equipment failure we had on the whole project. So we're going to get an amazing understanding of an S-type. We talked about the differences, the carbonaceous versus the stony. Bennu is carbonaceous, Apophis is stony, so a very different composition, but still a small rubble pile object. And what's going to be really cool is there should be a lot of tidal forces from the deep penetration into Earth's gravity well. And it probably will trigger some landslides and movement, some real active geology. So we'll get a chance to see how these rubble piles respond to tidal forces, which we weren't able to measure with Bennu. So different composition with the same instrument suite, orbit, remote sensing campaign, everything we did at Bennu except sample collection. And then even the final maneuver, we can't, because the surface interaction was so dynamic, we can't push TAGSAM down, but we're going to go ahead and drop the spacecraft and then just open up those thrusters and just scour the surface away, see how it responds, try to back out the regolith properties, and then most importantly, see what the subsurface looks like. We learned a lot about Bennu's what we call space weathering, how its spectrum changes over exposure time, because we got fresh material from the TAG event. We're going to do the same thing at Apophis. Thank you.
Okay, great. Well, thank you so much. Time, look at this. Sharp
Perfect.
0.
Yes.
Thank you so much.
Thank you, sir. And thank you. Thank you.
And if your time allows, people can.
Yeah, I'll be around if people want to come up and talk.
Sorry,
Yeah,
thank
my
you
pleasure.
so much. It was wonderful.
Thank you.